Today's speaker is Professor Ji-Hoon Han. So Ji-Hoon studied at the KAIST, good university. And then he did his PhD at the Crown, NYU, under Charlie Paskin. And then he went to Toronto he went to Samsung first, and then on the money. And then he decided to study further. So he moved back to Toronto under the Adam Stockbridge. Actually, some of you already know. And then he went to Dartmouth for postdoctor, and then he will be in his assistant professorship at SUNY Albany at this point. So his major is using the machine learning to serve the PDE. So today he will talk about that. So let's welcome Professor Han.
Thank you to all coming today, and thank you to the project team to having me here. Today I'm going to share my research work exploring the intersection between scientific computing, in particular the numerical PDE and machine learning. So this talk has a two-part. The first part, I will introduce how that machine learning can help to solve the PDE. So in particular, I will introduce the methods which incorporate the stochastic representation of the PDE solution, which state that how the particle time is related. So from that method, we can see some advantage in some large-scale problem, or great domain problem, or interface problem. And second part, in trying to reverse the perspective. So how the PDE can help to machine learning frameworks. In particular, in today's talk, I will introduce a method learning in between images. So if I have two images measured at two different times, then how one image evolves. So it estimates the intermediate state. Okay, let's get started. So I start some example of large scale or digital nature. So I bring some example related to some sustainability, which growing societal concern. So this is a appropriate bench near the park, or this is a appropriate cladding on the building exterior, such that appropriate means that many holes. Such design is not just for aesthetic, but also has a practical purpose. So for the case of the appropriate benches, that preparation allows that allow the rigid or rain drain easily, or that appropriate cladding is allow that some lightning or air circulation. So we reduce some dependency of some artificial some heating or cooling systems. And also some appropriate particle from the manufacturing process can be recycled to the new material, physically or chemically compressed to give some very heterogeneous material. So we have some very interesting modeling example that how the thermal distribution, heat distribution over that such appropriate material or heterogeneous material, or how that fluid flow such that operations. We can also find some multi-scale physical nature from our nature. So this is in ocean. There's high volume with small tidal motion and very complex patterns of the sea ice. And also here that many audience has a background in biology. So we can also find some multi-scale nature in biology. This is a membrane, and just that blue is the ion channel. So ion and or the particle diffuse through that channel. And here we are interested in question that how long does it take the particle moving out? So this is one of the modeling examples. We call the mean first pass time. So here's a sphere, and here that blue dot modeling that ion channel. So at this blue dot, it has a duration boundary, because that at this point it's already moving out, so it's zero. And another part is it cannot diffuse, so it reflected, so it's a moving average. So when solving this PDE on this sphere, we can see that here are very heterogeneous solutions. So So as you see that there are many needs for modeling the multi-scale problem, particularly some results in PD in multi-scale setting. So today method is one of that line of contribute that this is. Okay, let's start the math. So we have a PDE in that N is a differential operator and B is a boundary condition. So when we solve the PDE numerically, there are well-known discretization methods such as the finite difference method or finite element method. Finite difference method discretize the domain as a grid point, and using that grid point, we discretize the differential operator to get us an algebraic system of that solution at each grid point. So we solve that algebraic equation. Similarly, finite element method also considers the discretized domain, but the difference between the finite difference method is first is that it does not use directly the PD, but it uses the big formulation. And also finite element method considers some basis function. So goal is find some coefficient of the basis function from the discretization. So today talk I will focus on the different perspective using the neural network. So here you already know about the neural network is that a neural network is nothing but just nice parameterized function. Here I denote the parameter theta. So goal of this approach is that find some nice parameter that this representation is a solution of the PDE. And to search that optimal parameter, the difference between the previous method is that it does not require the discretization, but it uses a random sample for Monte Carlo sense. So depending on how to find such that nice parameter, there's a different method, such as the Gaussian method or the simple neural network, we abbreviate the PIN, and another is the different method. So this method is different depending on how they construct the loss function. So I guess that many people know about that simple neural network. So this is a one-more method. So basic simple neural network is very straightforward. So all of that basic simple neural network is first bring the neural network and to find parameter such that whenever you choose the point in the interior or boundary, it satisfies the PDE point-wise sense. So to find the parameter, so we construct the loss function in this that integral of that residual. It's an interior residual, PD residual is a boundary residual. Now we construct the loss function. We optimize that using some gradient descent method. So here is the integral equation. So we approximate this integral using some Monte Carlo integration using a random sample. So PIN has some integral loss and boundary loss. So here are some practical remarks that in the case of the PIN has a kind of two different objective functions. Because this two forms are different. So we call it as a multi-objective optimization. So PIN require to optimize this multi-objective. So in practical, sometimes we require some balancing between two terms to stabilize the train. This is the idea of how the PIN works. So today's method is, I mentioned, that using some stochastic representation of the PDE. So I will start with some simple Laplacian equation. So we have a Laplacian equation on the domain omega. And let's bring some n function u in the domain, the Laplace function, and bring some standard Brownian motion, say Vt. Then u of Vt is stochastic process, real value stochastic process, and using some iterodynamic stochastic version of the chain rule, we have that d of Vt is as a drift term and the mobility term. And as you see here, in drift term has that what is solved, that Laplace equation is a differential operator here. So if the solution is a U is a solution of this equation, then this process at 3 degree, then it's a margin. So from the martingale, we have a stochastic representation of the solution as u of x is expectation of u of t given v0 is x. This satisfies any time of t. So minimum of this representation is that first you choose any point in the domain, is a black dot. Solution at the black dot is nothing but just the averaging of the line locus during the time t. And distribution of the ds available one is by definition of the Brownian motion is a normal distribution. And as I said, you can choose any time t. So if you choose a time smaller, then it's a very narrow neighborhood, but still that Gaussian. And if time is longer, then workers starting from here, moving around, and at some point, at some time, out. So using some exit time, we can have this equation. So it's nothing but just that simulating the Brownian workers and collect the point at the boundary and taking the average. That is the element of the finite cache formula. So finite cache formula says the solution is represented by integral of the boundary values. This is kind of the boundary integral method. But today method we do not use the finite cache formula because simulate the particle exiting time is too long. So we just local representation of the solution.
Okay, can I ask?
Yeah, sure.
In the previous slide, you said about setup, but next slide, I can understand what was the setup.
Actually, here, this is a neural network.
Okay.
So this have a parameter there. But in this, I do not say anything about the neural network, but just
okay.
the PDE solution. The PDE can be represented by the standard parameter. So I did not introduce the neural network yet. Other questions? Okay, so more general cases, we add some advection term and the first one. Now, a little bit different. So previous case, we have a standard Brownian motion, but now, as we have advection term, so stochastic process is not just standard Brownian motion, but it has some tributary, same as the advection term. So using this stochastic process, we can have a stochastic representation of the PDE solutions. So difference is that general stochastic process, as it has a tributary term, and also we compensate the forcing term in here. But main idea is we can represent the solution using some stochastic process. So meaning of this one is that here the black dot is a one iterative point. The solution at this point is averaging of this sample, but this sample is not symmetric, right? Because it has a return, so it's skewed. But that, as you see, that symmetry is very, very helpful to simulating. So we try to change this x to non-determined standard Brownian motion, but we can using some harmonic Grosvenor theorem. It changed the measure to handling some distributed term. So using this measure change, we can represent the solution using standard Brownian motion, but we compensate that drift term is adding the edge term. So main idea is that we can represent the solution using some standard Brownian motion. That is the core idea of that format. So now we have a stochastic representation of the solution. Now we solve it numerically. So now we bring some neural network, say U of theta, and the goal of our method is that searching the parameter such that this neural network satisfies this representation. So let's bring the simple cases. So lopsided equation case, we consider the loss function as this. This is a residual of the representation. and then optimize that this loss function using gradient descent. But little bit different in optimization in our method. So in standard case, such as PIN, just directly compute the derivative in loss function. But here, that our method, our representation has here is unknown, and this is unknown, and this is also the expectation. So in here, there are many sample involved. So when you directly optimize this term, then it's very unstable. So how we tackle that this one is that actually this form is kind of the standard regression. So this is where we are interested in. This is a value of that. So we can see that this is standard regression and this is a target value label. So how we do is that first compute that this target value first using current state of the neural network, and then this update the setup such that this point has a value. So first compute the target and update the setup toward the target, and then update the target using some update neural network and follow the target. So we update the neural network and target value alternate. So this is the form of that reinforcement level. So, okay, so this is how we optimize. And now I do not mention very important part in solving the PDE. I didn't mention that. What is it? Boundary conditions. So in previous case, PIN case, we adding the boundary loss term corresponding to the boundary. But our method do not adding that boundary loss term, but we modify the stochastic process reflecting that boundary. So for the case of the usual boundary, so imagine that here's what we are interested in, and we simulate the Brownian motion, and once the Brownian particle is hitting the boundary, then we consider this as a kill that or obsolve that. In that manner, the sampling is changing. So if there's no boundary, this is symmetry, but near the boundary, the sampling is there. So solution at that black point is average of the yellow one and red one. And but that red, this is a boundary, and Dirichlet, we have information of the exact solution. So when you're taking the average, that exact information of the boundaries flow into the interior. In such manner, we training a neural network automatically satisfy that is boundary conditions. And for the case of that periodic boundary condition, say this part and this part is the periodic, then we consider that this boundary is connected. Just that treat that domain as just continuous. So here, particle is moving out through this boundary, then if we enter the here. Once that we simulating in this manner, then it automatically satisfies the periodic boundary condition without that loss term. And another that homogeneous normal boundary condition. Basically, that this term means that no flux through the boundary. That means that particle is reflected. So once the simulated particle is hitting the boundary, then it will reflect it. So that red one is reflected. So I actually change the distribution of the average. So in this manner, we tackling the boundary condition without that adding the loss terms. So here's a real sample particles. So this is the rectangular domain with some perforation, and here perforation has a normal boundary condition, and the boundary is a rectangular boundary is the Dirichlet. This is the real sample one. So here, as you see, that the particle is killed at the boundary. And for the case of Neumann, that this is a reflective, so it survived. Okay, so when you solve that this one, this first law is a FEM reference, and the second one is our method. I forgot to mention our method named DFLM. DFLM is derivative-free loss method, as you see that there's no derivative with respect to the input, different from the pin, right? So our method makes a DFL. So our method is the second law, and this is in the header. So this is very close to the FM numbers. And here, this is a control line, and as you see that this is control line is also belong to that boundary. That means that it's satisfied by that one conditions. Okay, more complicated preparation, we can also solve it with this. So here I emphasize the value of our method. So first, for the case of FEM, if the preparation is very complex, then it requires some more effort to discretize the domain, discrete the domain as there are more discretization here that small conversion like that. But because our method is random sample, so we do not need to such effort. Then you might ask about, oh, pin also have a random sample. Right, but for the case of pin, as I mentioned, that in this problem it has a lower boundary condition preparation and usually boundary condition boundary. And when you solve the pin, there are three different terms appear, right? So and when you train the pin, there might be require some balancing issue to stabilize that loss function. Our method is just single term, so we can avoid the risk of the rebalancing the loss function. This is the value of our method over that. Okay. This is interface problem. This also we can find the value of our method. So this is interface problem. Here we have two interfaces, two different conductivities. Different theories come along. This is a discontinuous. And here's the interface. We have one is jump condition, and the other is a loss condition. So we can handle this jump condition, loss condition easily, because that our method is not just focused on the point wise, but it focuses on relation between a point and their neighbor. So how we tackle the jump condition? Starting from this black dot, the brown particle moving out, brown particle is moving, and once it crosses the interface, then we can see the difference between the original point and the final destination. Depending on this relative location, we can add in or subtract this jump value, then we can automatically satisfy jump condition. Another loss continuity case is that if we have conductivity different, but if the conductivity is continuous, then it automatically satisfies. So simply modifying that this is continuous, it's automatically satisfying the loss continuity. How it works? Because this modification also changes the behavior of the stochastic process once it crosses the boundary. I mean the interface. So if just imagine that when you solve this problem, such as pin, only focus on the pointwise residue. How you can tackle this jump condition? It's not straightforward. But our method is that looking not just point, but also looking at around. So we can handle this interface problem. This is another value of our method. Okay, so as our method is a natural method, so as you know that there are many hyperparameters we have to tune in the training. So we also try to analyze that how the parameter affect the training. So in particular, we do some analysis related to the time step. This time is the Brownian time, not the Fisher time. This Brownian time and the number of samples. How much sample we draw. So if time is increased, that the difference is that time is increased, that is wider neighbor. And if number of samples is increased, it more depth. How these two terms affect the training process. Okay, so first result is about the bias. So as you see that the loss function, original loss function is continuous integral, but we approximate the integral loss using some sample. So we have empirical loss, and unfortunately our method, our empirical loss has a bias. So and bias term is proportional to the time and inverse proportional to the number sample, and the size is depending on the gradient of that the solution gradient of the u. So when you choose that parameter, you have to consider that this ratio, the children ns, appropriately. And also another remark of that this analysis is that actually I like this part. So we have a bias, and what effect of the bias in training? We know that averaging of the empirical loss term expectation is different than the loss term, and we have a bias term, but how it affect the loss, how it affect the training. Actually, this bias term effect as a regularization. And as you see that this regularization term depending on the size of the gradient. That means regularize the size of gradient. That means function is smooth. Right? But intuitively, our method is point and averaging. Averaging kind of is smooth. If you are familiar with the image analysis, blurring is kind of the average. So we can see that by averaging gives smoothing, this analysis see that effect of that this bias smoothing straightforward.
Can I ask a quick question?
Yeah,
What
sure.
is a capital NS?
Oh, yeah. Capital NS is that number of the sample when you draw from that each point.
Thank you.
Other questions? Yeah. So another is that each iteration your network is updated, and this analysis is that how much the updated happens. So here that UN is your net state at nth iteration, that n plus 1 is the next step approximation, and how we did. So we can see that the difference is proportional to time. That means that if time is longer than the much updated time. If time is too small, then update is very slow. So, for example, and actually, I do not explain all the detail, but actually, when you the averaging, our stochastic representation is nothing but just that convolution of that some kernel and taking some linear term. So it is kind of that iteration of the convolution. We can understand our method as an iteration of the convolution. And for the case of the simple Laplace equation, that means that it convolutes that Gaussian. But if time is too small, the kernel goes to the delta function. That means when you're updating the target is itself. So it does not improve that. So in this analysis, you can see that this is a different from the classical find a different method. Find a different method as mesh size smaller is better. But it's compute heavy. But in our method, if time is too small, that learning doesn't happen. This is the main difference that find a different method in our method. Okay. So let's speed up. Okay. So before we move on the multi-scale problem, I remind some rationale of the P and the FLN. So our method is that focus on point to neighbor relation. How that this point is related to another. But for the case of pin, only focus on that PD relation. And for the case of pin, then how they run that relation between the neighbor is not directly, but indirectly through that neural network. So in this sense, the pin is very dependent on that neural network. Another comment of this method, our method, is that relation between a point and neighbor is very similar to find a different method. You find a different method, just imagine the grid point and Laplacian operator. Laplacian operator, we see that one point is the averaging of that other nearby 4 point. So in this manner, our method is very similar to the find a different method. Okay, let's move on to the vertical scale. So this is a standard vertical scale problem. It's a variable coefficient quality equation. So here the coefficient is depending on some sine, cosine, and we have scale epsilon. If epsilon is smaller, then heavily oscillation happens. So in this settings, we need to solve some PDE. Just imagine that solving to find a different method or find element method. Then you need some very fine meshes to resolve that small oscillations. So actually computationally tractable. Also, when you solve the other method, the pin, then actually it's not easy to capture the shape. Exact solution looks like the bell shape, but it actually running never happens. So actually, this is the exact solution of this problem. So the solution is the yellow one, is overall the bell shape. And when you zoom in, then there is some small oscillations. And that green, that black one is corresponding to the macroscopic behavior of that original solution. We call that this black one is homogenized solution. And as this such the simple bell-shaped solution is from some constant coefficient, that we call the homogeneous coefficient. So in multi-scale community, they are interesting. Not only just that, of course, they're capturing all the macroscopic and microscopic behavior is what desired, but it's very hard to capture all of things. So at least they want to capture the macroscopic. So there is some homogenized theory to compute that this coefficient. Actually, this compute is not simple. You just imagine. You might just guess that just simply taking the averaging of this coefficient, but actually it's not, because when you're taking the average of this one, this is a 1. A solution corresponding to 1 is just that green. It's very different. And another that neural network approach to solving some such vertical problem. Many methods just following that based on that homogenized theory. But our goal is not using directly that distinct in this theory, but fully data driven. So to explain the detail, we call that our loss term is here, our representation here, and I will introduce some micro time to taking the integral of that original time step. I call that, from now on, I call it this macro time, and the small digits micro time. Then, macro time is a computational cost. And of course, we want to make it that macro time is the numerator as small as possible, and micro time, the denominator, make it as large as possible. So, first, for the case of the upper bound of micro time step, we have to consider the local variation of the one period. So we choose that micro time to capture that small local variations. So n0 is discrete number of discretization to capture that shape. From that, we can find some upper bound. And for the case of lower bound, there's a periodic cases. So all of the information is periodic. So this macro time is determine the size of the neighbor, how much power we have to give. And our conjecture is that one period is enough. The time step should be covered the one period. That is enough. So this is gives some lower bound. So using this upper bound and lower bound, we can see that the ratio of the macro over micro does not depend on that scale, but only depend on that M0, that is the shape of the period. So here are the two different scale. The stabilizing step is the ratio the same. So using this one, we solve that multiple problem. So as you see that it kept the black one is our method from our method, and it captured that microscopic behavior. And here's a comparison between the other method. So as you see that even standard versatile perceptron can solve it, and trying another very nice structure. It improved, but not enough. But our method is using standard versatile perceptron and find some microscopic behavior very easily. And here I want to emphasize that iteration is different. Scale is different. Our method is just 10 times the exercise. Even the more complicated, in the setting of the more highly oscillating, and our method working well. Okay. Skip that nonlinear case, it works, and skip that. And this is another type of homogenization. So previous case, coefficient is very highly oscillating. But in that case, there are many corporations. The coefficient is just one, very simple. So multi-scale behavior comes from not just coefficient, but from that geometry of the geometry of the domain. So in this setting, and this is homogenized solution of in this setting, and this homogeneous solution is defined of all the domain. That is a limiting case is that the proportion is small and filled out all the domain, and it gives them just original. And from that, our method, it captures the homogenized solutions. Okay. So, so far I just mentioned that elliptic cases, the steady state and diffusion domain. But now, currently we are on the way to develop our method. So now, recently I focus on more advection domain problem. So diffusion term is small, but advection term is relatively large. Then can we tackle such problem with our method? So this is one example of the icon equation. The other is the Borger's equation. So for the case of the icon equation is modeling some distance from the source term. So when you tackle the icon equation, we adding some small viscous term, generally called the vanishing viscous method, and very small, adding the small viscous term. And using this form, we have stochastic representation. And stochastic representation says how the information is propagated through, how the information propagates locally. So using this relation, we can solve that icon. Well, advantage of our method is that for the case of the vanished viscous method, if it's going to be very small, then standard method like the finite volume method, finite element method, it either solve the PD, but reducing that epsilon step by step, like 0.1, 0.01, 0.01. But our method does not require that such step, but just training one shot to solve that problem. And also, Borger's equation gives some like stochastic representation, and meaning of that this stochastic representation very resemble that you already know that method characteristic, but stochastic version of that characteristic method characteristics. So using this representation, we can also solve some reverse equations. Even that viscosity is very small, sharp pattern, but we can solve it. Okay, so this is a part one. Any questions? Alright. Let's move on to part two. So in this part, this is a case of that how that PDE can help that machine learning frame. So today's work is a project funded by the Office of Naval Research. Office of Naval Research are interesting how the CIs, the dynamics of the CIs, how the CIs move, how cracks generate, how they melt. So satellite moving around the Arctic region and collect the data. But this periodicity is quite long. So I want to measure, but we don't know exactly how that the details in between. So our goal is that estimate how that this inner condition is evolved to that destinations. Okay, so of course that mathematically is not very close because there are a lot of scenarios. So our goal is generate some evolution, but this is more physical. And also, if possible, we can interpret that the result. This is our goal with this project. Okay. So there are only a few related works. So there are a lot of methods that name of the video prediction. There are a lot of the time-lapse history of the frame, and from that history, find a pattern to estimate the future. But this project is only 2 images given. How one image evolves so much. So related to that, we find some using some method using the optimal transport theory. So optimal transport is nothing but if you have two different probability distribution, then optimal transport is how that this efficiently transport that this property mass to a metric. And metric is a vector spanning distance. So this is only one method we found it. So we compared our method to these approaches. This is the main idea of our method. So just imagine that taking the snapshot at our region at a specific time. That at that time there are corresponding some environmental state, such as the sea surface temperature, or just temperature, or wind speed. And we can view that the snapshot is kind of the function of such that environmental state. We can view that this snapshot is a function of that. Okay, so and such environmental state is more familiar for us because that this is physically evolved. So we can use some physical word like P. So for the case of the sea surface temperature or general temperature, it's kind of diffusion. For the case of the wind speed, like subtraction. So our learning flow is do not directly learn that interface from t0 to xt1, but detour that physical latent space. And this latent variable is evolved as some physical like the PDE. That's the main idea. So of course that if we know about the mapping between two spaces, then it's straightforward. But because we don't know, so we put on some neural network and encoding and decoding, and also bring some PDE model and running some parameter in the PDE using another method. So using this flow, we train using the given data, and we see the evolution. So how it works? So actually in this work, we simply using, there are many possibilities to put on some PDE model. In this work, we only consider mode of action equations. So we assume that internally it involves following mode of actions. So flow is from this image and encoding to the latent spaces. And once the latent space arrive here, that evolve following that mode of action equation. And once reach that terminal T1, then decoding to the latent space to image space to reach that final destination. And because we have evolution in the latent spaces, and we learn that encoding and decoding. So in here, decoding, using the decoding, so we find the corresponding evolution in image spaces. So as you see that we have only two images, but actually in such the CI's image, the size is huge, fortunately. So our data is temporally sparse, but spatially abundant. So we're using some like patch to find some, because only have two labels, but using the patch we make some pair of a lot of patches. So we learn that this patch to patch dynamics. And loss term is like some first the loss dynamics is starting from here, it should be reached to here. This is a corresponding dynamics. And autoencoder is that original flow is like that. We impose that this map, when you're applying this map to here, that is satisfied here, and vice versa. So this is kind of the autoencoder realization. And actually this is not necessary. In mode of action equation, we had to learn that mode of action vector field, but we assume that that vector field is smooth, as that making more physically makes sense. Okay, so this is the first example. This is a time t0, and this is time t1. And imagine that how it evolved from one to another. When you see the result, it's very straightforward. So here is the result from our method. So it's just that transition diagram. And this is corresponding to latent spaces, and this is a vector fitted one. I forgot to mention that typically that in machine learning and machine learning framework, we call the latent spaces lower dimensional representation of data. But in this method, we consider the latent spaces as the same as the original image. The reason is that once we have a result from the latent dynamics, we have a vector field. Using this vector field, we infer that original dynamics in the image. If this is too small and if it's not organized, well, even we have some vector field, we cannot using this vector field to infer the original dynamics. This is why we use the latent space the same as that original image spaces. But of course, that possibly you can use that half size of the rectangular size. But the point is that you can put on some data type as image, and you can infer that result from the latent dynamics from original dynamics. And this is from the Wolfram transport. You see that you cannot see the first kind of transition. Actually, we cannot say that our case is right and this is wrong. That's not good. It was possible. But I guess that this is unfeasible. And another point is that our method is that generating through boundary and disappear through the boundary. But optimal transport cannot capture that such behavior because that optimal transport is kind of we have two probability distribution, and optimal transport consider only relocation of the mass within that probability. So it cannot consider some generation or disappear. So this is that. I mean that in application of this, optimal transport is not a good choice. And this is another example. And as you see here, there's some crack, no crack, but here no crack, and there's some crack. And guess how people from X0 to X1. This is a river. This is a rotational dynamics. So overall, that is a counterclockwise rotation, and as you see that the crack disappear, and then another crack generated, not the simultaneously. And we can see that, and also some distracted field gives some it confirms that it's a rotation dynamics. And we can quantitatively interpret that during the rotation, some force flow that in this way to compress the ice, and that impact is propagate the remaining part, sequentially generate that this crack and this one. And optimal transport is, as you see that, as similar to the previous case, just simply interpolating the two things. And optimal transport actually, the standard optimal transport never capture the rotation, right? Because that rotation is not optimal, right, to moving that mass, right? Just straight line is that. So rotation is hard to capture from that optimal transport. Okay, so yeah, so this is a last slide. I prepared some virtual work related to the part 1. So, because this is the main research for me. So, yeah. So there are many future work I consider for the DFLM. First one is that we are now expanding our method to the time dependent cases. I see that over diffusion is time dependent, and eventually I want to reach that to solve the Navier equation, so fluid dynamics. And because when I was the PhD student, I work on some fluid structure. I studied the fluid structure interaction using the immersion boundary. So I want back to that simulation using new method. And another thing is that for advanced boundary condition. So today I introduced the usual or theory or homogeneous limit condition, but there are more general boundary conditions, such as the Robin boundary condition or Stefan type problem. Stefan type problem is modeling, and here's because of water as well as ice, and when you put in the water and ice, then this boundary is moved. And this is a kind of moving boundary. And maybe there is some real particle dynamics near here. So using some internal particle dynamics to simulating that this moving particle. This is a very interesting question, interesting modeling problem. And third one is about the anomalous diffusion or the fractional PDE. So today I mentioned the standard diffusion. Diffusion using the standard Brownian motion. Standard diffusion means that averaging distance of the particle is linear. Standard Brownian motion case is that mean squared distance is linear in time. But in nature, is not the only one. So it might be dependent on some not linear but power of the alpha like 0.5 or scalar. So this is related to the anomalous diffusion, and actually that PDE version is one of the fractional PDE, like the Laplacian over the half. And we can tackle that this fractional PDE or anomalous diffusion using some particle dynamics as we did. And finally, this is our one of the ultimate goal of that PDE solver. So advantage of the neural network approach is that mesh free. You do not require the generator mesh and easily implement. This is one of the big advantages of the neural network. But disadvantage of the neural network is that it's very hard to reproduce because it depends on optimization, it depends on the random state, and conversion does not guarantee. It's very hard to reach. I mean that it's very irreproducible. This is it's very controversial in PD and PD community that one part is classical find a different dynamic element or find a polymath that another type of neural network UV. So I want to bring some advantage of the neural network that is a mesh free, but I want to remove that neural network. So non-parametric PD solver, then this is the best one, right? So actually this is not far future work, but I just simply recall that our method is that iteration of that some convolution. And as I said, updating target following neural network, updating target following neural network. But actually we already know the target. It does not require the neural network to following that target. So in this manner, we have some preliminary work that without the neural network, but still the mesh free, we can solve the Laplace equation. So we success to solve that this one. So I build up this approach to more general PDE solve. Okay, this is my future work. Thank you for listening.
Okay, so it's Q&A time. Please feel free to ask any question. Yeah, go ahead.
So in order to apply your first part, do we need diffusion in our
So currently that utility cases, so diffusion, I mean, in diffusion cases, we can have a stochastic representation, like some averaging like that. So yeah, in diffusion case, we can solve it. And also, even we do not have like some eigenline equation, there is no diffusion. But we can of course to get the representation it requires that the diffusion term, but as you see that very small diffusion term to get the representation, and resulting formula is giving some particle dynamics. Right? So I can say that even there is no diffusion, we can try to solve using the formula. But I cannot say that I can solve the whole PDE problem. Yeah.
Can I ask a question?
Yep.
It is very similar to this question. When you do that rotation, when you reproduce the rotation image,
Yeah.
that case, then what was your PE that was a simple.
Simple abstraction.
Uh,
Yeah. So here another comment of that. When I gave a talk about this that why the PDE mode is too simple. We can of course we can edit the diffusion term, so diffusion and edit the fraction and other type of diffusion type. But actually when you try diffusion, even the you might just thought that diffusion is very simple, so it's very easy. But actually, it is different story in training. It's very hard to learn the diffusion coefficient. So that is why we only put on some abstraction terms. But I can add some value of the simple one. Even this is a simple, but abstraction is very natural because that we want to know about motion of the image. And this vector field is very full information. This is another comment. And the other is that, so we can understand that the main of latent spaces only extract the main lane of action physical quantity which is affected, and remaining part is covered by the encoding and decoding. And this is very similar, and abstraction is kind of linear. And actually, I'm not expert, but in dynamic system there is a Kuhlmann operator. That, as I know that main idea of the Kuhlmann operator is that even the very highly complicated dynamics you can using some linearize. So in that sense, our method is a little bit similar to that the rational of the Kuhlmann operator. There's another comment about that.
Any other question?
Maybe I missed.
Yeah.
Alright. What is the boundary condition of train?
Oh, yeah, here, verification. Low boundary. Yeah, free boundary. So that is why we can see that there is some inflow and vector fields. Yeah, so see the vector field is inward. That means that when you're simulating that action equation, there is some interpolation toward that inward. So yeah, the method of replication is the free boundary.
Any other?
Then it's a this simple question. Then when you decide the boundary condition, you should see the two image and you need to decide yourself what will be the boundary before you simulation.
I mean, of course, it depends on the application. But I guess that here, put on some visualities. I did not sure. And even the put on some movement, not sure. Yeah, depends on. Of course, that if we have today's I just gave me some CI dynamics, but if we have a two image about that, like two particle moving around some constraint, and there's a reflected. In that case, we can put on some order multiplication.
Thank you.
Yeah. It depends on.
있습니까? 그러면
So can I, so is it publicly accessible? Can I use this?
You mean the code?
Yeah.
If you want to, then yeah, I can share. But we do not put on some stuff like that. Yeah.
you want to use it?
Yeah.
The things.
Yes.
We actually, I also try to send some cell image, cell locomotion, and I can try.
I think that, yeah.
What would you want the single cell velocity?
Yeah, single cell. So people want to find some velocity field in the load meter embedding of a single cell RNA sequence of data.
Yes.
And then they try to find some cell dynamics
Yeah.
in there. So I want to try.
Any other question? Okay, then let's thank the speaker. 혹시 개별 미팅을 하고 싶으신 분이 계시면 알고 있어요. 한 10분에서 15분 정도 시간 있습니다. 네. 하십시오.
네, 개별.
네, 다음에 또 하고 싶으신 분 계세요?